Okay, good morning, everyone. Sorry about the delay, but that was sort of out of our hands, and we've hopefully adjusted accordingly and haven't lost too many people along the way. It's our pleasure to introduce this morning Khulekani Khumalo. Khulekani is a Zimbabwean, and he's been in South Africa for some time now. I think he finished his schooling in Johannesburg, and he's busy doing his PhD, which we're going to hear about today. So he did his BSc Geology at Wits and a BSc Honours in Geochemistry, investigating the formation of the bushveld magnetites using iron isotopes. And he's currently, as he said, if some of you are on the call, writing up his PhD study investigating the mantle sources and crustal contamination of the Ventersdorp large igneous province using strontium, neodymium, and hafnium isotopes. So thanks, KK. We really look forward to your presentation, and nice to have some of your other colleagues and students on the call, and good luck. Over to you.
All right, thank you. Thank you for this opportunity. I am Khulekani Khumalo. Today, I will present the sources of the Ventersdorp LIPs. So first of all, I'm going to introduce the concept of large igneous provinces. These are magmas that have been compressed in a short period, usually 5 million years, but they can go up to 50 million years. And they can be compressed as oceanic flood basalts, dark swamps, seal complexes, continental flood basalts, which what I'll be focusing on today. And also they can be compressed as layered intrusions, such as the famous bushveld complex. Multiple sources have been proposed for this magmatism, large magmatisms for the LIPs. And these include the mantle plumes originating either from the core mantle boundary or mantle transition zones. The other source is the subcontinental lithospheric mantle, and also the convecting mantle, the asthenospheric mantle. But today I'm going to focus on the comariates of the Neo-Archean Ventersdorp continental flood basalts, the Western area comariates. The reason why I'm focusing on the comariates today is because studying of these high magnesium lavas will give insights into the mantle source of the Ventersdorp, since we assume that these ultramathics possess geochemical signatures that are similar to their source, and also they represent the least crustal contaminated units of the sequence. So before I get into the Western area comariates, I'm gonna just mention a few issues that we have with the Ventersdorp LIP. So recent studies are proposing a subdivision of the Ventersdorp sequence into 3 LIPs, meaning that there were multiple magmatism events at 2.78 billion years ago for the Klip-Riefersberg LIP, and also at 2.72 for the Bloodberg LIP, and then lastly the 2.65 Allen Ridge LIP. Instead of one large magmatism event forming the Ventersdorp large igneous province as we have known in the previous years, but the recent studies are proposing a subdivision of this LIP. And also we need more work on the dating of the units so that we can be able to solve this problem of the number of LIPs in the Ventersdorp, and also be confident with the eruption rates and dates. And also, one of the issues that have risen with the Ventersdorp sequence is that there's been some correlation of the Ventersdorp LIP on the Calval craton, correlating it to the Fortescue LIP on the Pilbara craton in Australia. And from this, using paleomagnetic and cryonological constraints, as well as lithostratigraphy and geochemistry correlations, they have proposed a supercraton or supercontinental supercontinent named Valbara, combining the Capval craton together with the Pilbara craton, and they've come up with a lot of models, such as the ones that I've shown in here, showing that these two cratons were once together during the formation of the Ventersdorp and the Fortescue magmatism. And another issue that I'm gonna look into today or mention is that there are studies where they mention the Western area lavas as comariates, true comariates, and other studies that mention lavas as comaritic basalts. So here I'm trying to show you that in this study, I'm going to refer to these lavas as the true comariates. This is because looking at the simple and strict definition of comariates, comariates are ultramafic volcanic rocks with magnesium oxide content greater than 18 weight percentage, and usually they have diagnostic spinifex texture. And this is what we see in the Western area lavas. So therefore, we will refer to these lavas as the true comariates. So moving into the Western area formation, the Western area lavas form part of the Klip-Rufus-Beck group, the earlier magmatism event of the Ventersdorp sequence. They are the first lava sequence of the group. So the Klip-Rufus-Beck group has been dated to be 2.78 billion years old. We are dating the intrusions that are thought to be the feeders of the Ventersdorp. And the Western area lavas are preserved in the deepest parts of the Ventersdorp basin. This is due to the uneven topography of the basin during the eruption. And also we can say that the lavas are at least 50 meters thick, and they have magnesium content that goes up to 25 weight percentage. This is for the samples that we've analyzed. So looking at the top plot, the green stars, these are the samples that we've analyzed in the study for the Western area lavas. And you can see that they range from 16 magnesium weight percentage to about 25 weight percentage. Mostly samples are classified as comariates. And typically, these rocks have higher titanium oxide content than the typical Barbertine comariates that is shown as the rectangle. Yeah. And also, there hasn't been much dating of the units, but we can H bracket the Western area lavas using the Albertine dates and VCR dates, Ventersdorp contact reef dates obtained by Bartin et al. In 1980. They dated the Venter post to be 2.78, and the Albertine dated by Armstrong and Stamnija in 2017 to be 2.8. So the 2.714 date by Armstrong has been discarded due to the common late that has been attributed to this date. So Stamnija re-evaluated the sample and dated the sample to be 2.8. Therefore, we can confidently say that the Western area lavas are between 2.78 and 2.76 billion years old. So we have sample locations. So the samples that we are dealing with come from the eastern part of the craton in Mpumalanga. So the boreholes are located northwest of the Secunda town in Mpumalanga. There's borehole E1, E3, E4, and E5. These samples have been studied by the colleagues of Professor T.S. McCarthy here at this. And so from the drill core material that we have, we also made some thin sections, but I must warn you guys that these thin sections are quite traumatic, especially for someone who was coming from analyzing the fresh bushveld thin sections. They are too disturbing for someone who's not used to metamorphic rocks. So on the far left, I've put in the borehole log of E5. Here we see a commodite flow, which includes cumulate zones, porphyritic zone, and spinifex zones, and also a chill margin at micro spinifex zone that is followed by another cumulate zone. So this is a typical commodite flow. Here I've put in XPL images of the samples coming from this level at a cumulate zone. Here what we see phenocryst rich pockets that are surrounded by actinolite rich matrix, probably secondary actinolite. And within these phenocryst pockets, we see euhedral forms of that are probably olivine, used to be olivine phenocryst. And the shore alignment or preferred orientation, you can see on the far left image that there is some alignment of this phenocryst. And also there's some veins that are parallel to the alignment. It is difficult to identify the phases using the transmitted light. So we went on and used the TIMA, a mineral analyzer machine. And these phenocrysts were identified as chlorite, here shown as the purple phenocryst, and that are hosted by the actinolite. So therefore we say that this cumulate zone is composed of or consists of chloritized olivine. Moving on to another level of cumulate, I've shown here I'm showing an XPL image of a cumulate zone. You can't clearly see what's going on or the phases. So we went on and again we used the TIMA imaging to identify minerals or the phases. So what we see in that zone is that there is some relic within the phenocryst. There is some relic olivine that is being replaced by enstatite, represented by the blue color. That is in turn being replaced by chlorite, represented by the purple color. And these phenocrysts are still hosted within an actinolite-rich matrix. So we refer to this zone as the olivine or chloritized olivine cumulate zone. And then we move into the porphyritic zone, lava zone. Here, these are the PPL images. So on the left, this is the PPL image in which we can see the decrease in the abundance of the phenocryst. And I've zoomed in. We can look into the top right image. Here, looking at the form or the shape of the phenocryst, we can clearly see that these were or used to be olivine phenocryst, highly fractured subhedral form of olivine. But we see that these phenocrysts have been silicified. Under the TIMA imaging, we observe that the phenocrysts have been silicified. They are identified as quartz grains that have calcite infilled fractures, and some fractures are still enstatite. And also observe an increase in the abundance of tatanite. And there's some chlorite and enstatite, represented as blue, still hosted by an actinolite-rich matrix occurrence. And again, in this image, we can still see a preferred orientation of this phenocryst alignment, probably indicating to the flow of the lavas. And then we move into a macro Spinifex texture. the top image here, that's the XPL image of one of the Spinifex samples, and not easy to identify the phases. So we used again the TIMA mineral analyzer to identify the phases. So what we see is that the Spinifex needles are secondary actinolite, and in between these needles there is relict olivine represented by the green specks, relict enstatite represented by the blue specks, and then the purple, that will be the chloride. And then going further down into the borehole, we move into a macro Spinifex zone. So there's some finding of the Spinifex. What we observe here is that we come across relatively fresh, preserved phenocrysts that have been identified as cyanopyroxenes, both by TIMA and EPMA work analysis. And these phenocrysts, cyanopyroxene phenocrysts, identified as diopside, they partly show sepitization, and also they are highly fractured. This is probably the most freshest phenocrysts that we have come across in our samples for the Western area lavas. And then moving into the cumulate, pyroxene cumulate. So on the right, I've shown the relatively fresh phenocryst, highly fractured. And then on the left, I'm showing highly altered, not so fresh compared to the ones that I've shown on the right. These are extensively altered cumulate zone. But you can clearly see that it's coarser grained and it is a cumulate zone. So that's it for borehole E5. And then in other boreholes, that will be borehole E3 and E4. We see different textures. Here we mostly see sort of coarse recrystallized amphiboles, actinolite and tremolite crystals, grains, and also an increase in the abundance of titanite, shown as these dark brown specks. So there is some difference in these boreholes. And again, we were not able to correlate the boreholes laterally due to the limited information that we have on these boreholes. We could be looking at different sections of this high magnesium lava sequences. That's why we are not observing similar textures. So that's it for the petrography analysis. We move into the geochemistry of these high magnesium lava sequences. In terms of the major element variations with magnesium oxide, there is a lot of scattering. Probably this is due to multiple events of hydrothermal alterations. But looking at the titanium oxide and calcium oxide, there is some good variation, good correlation with magnesium, probably indicating olivine accumulation. And this is also observed in the trace element of these whole rock major elements. So again, here I've plotted nickel and chromium against magnesium oxide. What we observe is fairly to good correlation with magnesium oxide, indicating olivine accumulation is observed in the nickel and chromium. But this is just all the samples that we have analyzed. But is there anything that we can see with the stratigraphic variations in terms of geochemistry? So I focused again on the borehole E5 to see if we can see any variations. On the slide, I'm showing the major element variations of across the borehole E5. What we observe with the magnesium oxide, we see that we observe high magnesium oxide content at the Microspinifex zone and again around the olivine cumulate zone. And we also observe some differentiation or evolution of the lavas to lower magnesium oxide content. And for the calcium oxide, we observe the high calcium oxide content at the porphyritic lava, where we observe the silicified phenocryst, and again around the olivine cumulate. And we attribute this high content to the calcite veining and quartz veining that were observed in that zone, and also the calcite fractures within the phenocryst of the porphyritic lava. Moving into the trace element, we observe high nickel contents again at the zones where we observed high magnesium content, which are olivine cumulate zone and the Microspinifex zone. And we also observe high chromium content at the olivine cumulate and also at the pyroxene cumulate zone. So we went further and tried to investigate where these elements are hosted within these zones. So for the olivine cumulate zone, we observed that the magnesium is mainly hosted within the phenocryst. You can see the mapping of the phenocryst by the magnesium content. And for chrome, there's very low content. We couldn't map out where the chrome is mostly hosted. And then for calcium, we see tiny specks that have high calcium content within the phenocryst. Probably those are the fractures within the olivines. And then moving into the investigating the Spinifex zones, we see that the magnesium is hosted within the matrix, not in the actinolite needles, but in the olivine and statite and chloride phases within the matrix. And the calcium and chromium specks are also observed in the matrix. And then moving into the pyroxene cumulate, we see that there's higher magnesium content compared to the phenocryst. And the chromium and calcium, they easily map out the pyroxenes. There's high chromium content within the pyroxenes and also high calcium content within the pyroxenes compared to the matrix. So that was it for the element distribution or element major and trace element distribution of the lavas. We went on and tried to assess the alteration in metamorphism before we move into the isotope work. So on this slide, I'm showing a calcite and chloride rich vein around the pyroxene zone. And then on the far right, I'm showing the calcite and quartz veining across the olivine, chloritized olivine zone. And in the middle, I'm showing the silicified phenocryst that probably were olivine, and through multiple alterations, they've been converted into quartz-rich phenocryst or silica-rich phenocryst. And these indicate to carbon-rich fluids, silica-rich fluids, and hydroxide-rich fluids that alter these rocks. So for hydration, we shall see phases that indicate hydration. The serpentine, or mostly observed around the pyroxene cumulate zone. There is talc. Also, we observe the chloratized spinocrest in the olivine cumulate, and also high abundance of titanite, probably recrystallized secondary titanite, shown here as these brown phases. And titanite is a rare earth element rich phase. And again, we also observed amphiboles, actinolite and tremolites. You can see that they are perfectly recrystallized during these alterations and metamorphism. And also what we observe in the overlaying unit, which is the Albertine formation, we also observed epidotes. And this is also another rare earth element rich phase. So moving into the incompatibles, we primarily see that these comarites are super enriched in the incompatibles than usual comarites where the comarites of the barberine will float around this zone. But with the western area, they are super enriched in these rare earth elements. So we attribute this enrichment to the abundance of the rare earth element carrier in minerals such as the titanite and epidote. This is probably due to the hydrothermal fluids that complex with rare earth elements such as carbonate fluids, and these fluids would have brought in additional rare earth elements. And possible sources for these carbonate fluids will be the overlying transfer supergroup and the hydrothermal system would have been triggered by probably the Ongeluk magmatism or Bushveld magmatism or any later large magmatism that would have been able to trigger and mobilize the rare earth elements. And within these samples, there are a few samples that display unusual rare earth element patterns. And moving on to the multi-element plot, what we observe, we observe a negative anomalies of the mobile elements, such as the rubidium, barium, and strontium. These were probably lost during the alteration events. But again, we also observe negative anomalies that we think are primary signatures, such as titanium negative anomalies, niobium and tantalum negative anomalies. But with these niobium, we see that there is some samples that show larger anomalies, probably due to a small degree of mobilization of this element post-magmatic. So looking at it with the titanium, we have plotted titanium against the zirconium to test the mobility of titanium, assuming that zirconium was immobile during the alteration events. And with titanium, we see a moderate to good correlation of 0.75 compared to niobium that is a correlation of 0.12. This is probably due to some of the samples that experience higher extent of alteration compared to other samples. But generally, we say that these negative anomalies that we observe in the niobium and titanium are primary signatures, not post-magmatic signatures. So we have done looking into the alteration and metamorphism effects of the lavas. Now we can look into the strontium, neodymium, hafnium isotopes. So previously I've shown that the mobile rubidium and strontium were mobilized, so there should be some care in analyzing the rubidium and strontium system. So what we've analyzed for the Western area lavas, that the epsilon neodymium composition ranges from negative 1.7 to positive 2.2 at 2.78 billion years. This is the first data for the Western area Khumarites, and previous studies have analyzed the overlying formations of the Key Riversberg, and their epsilon neodymium composition at 2.78 will be negative 0.3 to positive 1.1. So we have introduced new data for this Ventersdorp group. And again, on this plot, we see that there is some scattering of the initial strong-term ratios. This is attributed to the alteration that was observed and analyzed in the previous slides. And again, there is some trends probably due to contamination by some high evolved contaminants. And again, the isotope dilution was done here at Wits, and the mass spectrometry was done at UJ. On the slide, I'm showing the epsilon hafnium and against the epsilon neodymium composition of the Western area samples. And what we've analyzed, we see that the Western area lavas have epsilon hafnium ranging from negative 1.8 to 2.3 to positive 3.6 at 2.78 billion years ago. And what we observe is the decoupling of neodymium and hafnium isotopes. By decoupling, this is an unexpected relationship between neodymium and hafnium isotopes. And what is expected for the mantle samples or mantle array? We expect the samples to form a positive array instead of what we observe with the Western area, a negative array, what we refer to as decoupling. And this decoupling could be either a primary or secondary signature, and we will look into that in the following slides. And one thing that we observed with the neodymium isotopes together with the rare earth elements, we observed that there's two groups of light rare earth element slopes, one with steep slopes and another with fairly flat or gentle light rare earth element slopes. And the steep slopes correspond to samples that have positive epsilon neodymium composition, and the fairly flat correspond to samples that have negative epsilon neodymium compositions. So this could mean that the hydrothermal alteration events could have altered the neodymium isotope compositions, which could be which could compromise our study. So we will have to look into that. Okay. So just to show you that the alterations did not really alter the neodymium isotopes to a great extent, I'm going, let's analyze two samples, samples RR505 and sample RR503. Both samples have positive epsilon neodymium values, however, they show different light rare earth element slopes. And sample RR505 has high abundance of titanite, shown as these brownish, dark brown specks. Titanite is a rare earth element rich phase. And then looking into the sample RR503, we don't see any titanite or high abundance of titanite. Thus, we have differing light rare earth element slopes. So if we attribute to the high abundance of titanite to hydrothermal alterations that brought in additional incompatibles, then we can confidently say that that alteration or addition of neodymium into the samples did not affect the isotopic compositions of neodymium, since these two samples show similar compositions. Therefore, we can say that there was minimal disturbance of the isotopic system. On this slide, I'm going to try to look into the variations of these isotope composition. So for epsilon neodymium against the initial strontium ratios, we see two clusters, and these clusters they also correspond to the boreholes. So this far left cluster corresponds to samples that are from borehole E4 and E3, and the far right cluster are samples from borehole E5. So what this means is that there is some lateral and vertical variations in the degrees of alteration, therefore different effects on the rubidium and strontium compositions, isotopic compositions. And special variations in chemical composition have been reported by Myers et al. In their 1990 report. And we can clearly see that these boreholes, borehole E4 and borehole E3, are 10 to 20 kilometers away from borehole E5. So there could be some lateral variation in the alteration degrees within these boreholes, or vertical, you couldn't correlate these boreholes. And also there is an issue of this decoupling that we observed between the hafnium and neodymium isotopes. This could be a primary signature or secondary. By primary, if there is garnet in the sample, this could lead to decoupling. That's if the garnet is retained during partial melting. So lutetium partitions greater than hafnium into the garnet. This causes the decoupling between the two isotope systems. Or if there was any disturbance of neodymium system post-magmatic, this could cause this decoupling. But in our previous slides, we've shown that there was no significant alteration or disturbance of this system. So we attribute this decoupling to a garnet control in the source. So we've assessed the alteration and metamorphic effects of the on the isotopes and on the lavas. Now we can try to look into the crustal contamination of the lavas or the magmas. So on this image, I'm showing possible contaminants, plausible contaminants of the Western area magmas, except for the Bushveld complex since it's younger. So the Ventersdorp is shown as the blue areas, and the possible contaminants include the Johannesburg Dome, the ancient gneiss complexes, the Archean greenstones, such as the Barbertine, the Pongola supergroup, the Dominion group, and the Witwatersrand supergroup. Unfortunately, there isn't enough strontium, neodymium, hafnium data, isotopic data that is needed to model the crustal contamination. There is some few data in the literature that we've used. So what we've done here, I'm assessing crustal contamination by bulk isotope mixing. That will be bulk assimilation of crustal rocks. So looking at this plot, we see that the Western area plots are these green circles, solid circles. If we leave the samples to be where they're plotting, then using the depleted mantle at 2.78 billion years ago as their source, then there could be some contamination of these magmas towards a highly evolved contaminant by AFC. However, if we plot the drawback tonalites represented as the blue circles and drawback dome granites represented as highly evoked compositions, and also drag these samples back to where they will be if the strontium isotopic system was not altered. So plot around this green circle. From this, we can clearly see that the Western Wire lava magmas were at least 20% contaminated, volume by volume, contaminated by the tonalites, 30% by tonalites, and at least 20 or 15% contamination by volume by the drawback dome granites. And we've also plotted the dominant lavas reported in Hoffman, in Agangi et al. 2020. They only report the epsilon neodymium or neodymium isotope composition. We've plotted them around this position. And if the Western Wire commodities were contaminated by these units, then that would be a significant contamination, and we wouldn't expect to see the high magnesium content of the Western Wire lavas. Therefore, we don't think that the dominant lavas are contaminants of the Western Wire magma. Probably the drawback dome granites were the contaminants of the Western Wire magma. And here we've also plotted the 2.78 similar age as the Western Wire magmas, the Petersberg granites, and their magmatism is probably related to the Ventersdorp magmatism, and they show similar epsilon neodymium composition. We also assess the cluster contamination of using epsilon hafnium against epsilon neodymium. Here we have plotted the ancient gneiss complex gneisses, the Barberton 4-6, and the Dwalila greenstone ultramephics, and 4-6 reported by Hoffman 2020. From this, we clearly see that if the depleted mantle was the source at 2.78, the Western Wire lava magmas would have been at least 20% by volume contaminated by the Barberton 4-6 and the Asian gneiss complexes. And what we also observe is that the Western Wire lavas got closely to the Dwalila ultramephics. There is a possibility, since these are ultramephics and mephics, there is a possibility that the Western Wire magmas did assimilate these rocks. However, that will be a huge volume, which we don't want to take chances. And there are other evidences within the Klip-Riefersberg group that indicate to contamination, cluster contamination of the magmas. So in Armstrong et al., they report 2.9 billion year old zircon xenocrest within the Klip-Riefersberg lava. So there was definitely cluster contamination. Normally we hear that the lips, they're insignificant or they don't have cluster contamination, but in our study we see that there was some cluster contamination. So we can move further to, now that we have assessed the alteration effects, looked into the geochemistry, and then also looked into the isotopic compositions, we can now constrain the mantle source of the Western Wire lavas. So from our isotopic work, we can clearly see that the Western Wire lavas were derived from a depleted mantle source with some cluster contamination at 2.78, and that depleted mantle source was bearing garnet, and the garnet was retained during partial melting. This is the evidence for this garnet bearing source. It's the general light over heavy rare element enrichment. The aluminum depletion of the western rare comarites, shown here as the purple circles, and also the decoupling of the hafnium and neodymium isotopic. This serves as evidence of garnet control in the source during partial melting. So the constraints on the mantle source, now we've shown that it was a depleted mantle, and that source was bearing garnet, and the garnet was retained during partial melting. And knowing that the garnet was retained during partial melting, it was at a garnet stability zone, which is a deep source, and we'll need a multiplume to bring up that source. And therefore we propose a multiplume. And in our samples, we observed the negative niobium and tantalum anomalies. These are typical signatures of influence of a subducted material within the magmas. In our case, we propose that there was some subducted material that was entrained by the multiplume at 2.7, and this material, subducted material, transferred these anomalies into the multiplume. Plotting our samples on this plot, we see that the western area samples plot close to the OIP source, which is related to multiplumes, and also there might have been some deep crustal of exciting, which also supports the idea of the subducted material that influenced the multiplume. And these samples that plot on the left are attributed to the alteration or the mobilization of niobium within those samples. A model is that the Calva craton came about by subduction, and there was some subducted material that affected multiplumes beneath the Calva craton, modifying the multiplume, transferring the negative niobium and anomalies, as seen on the spider diagram or the multi-element diagram. So we are confident that the source of the Ventersdorp or the clip Riversberg lavas, through analyzing the western area comarites, was multiplume. To test this multiplume model, we look into the evidence that we have here on the Calva craton. So there was a domal uplift is predicted when there's an arrival of a multiplume beneath a craton. And in our case on the Calva craton, the domal uplift has been indicated by the Ventersdorp contact rift sediments. And also the arrival of multiplume initiates rifting, continental rifting, and we do have the northeast southwest trending Ventersdorp rift system. And again, the occurrence of the high temperature, high magnesium western area magmas in the clip Riversberg at the base indicates to the magmas as the first or early melting products of this multiplume. So to conclude, using the western area comarites, we propose that the clip Riversberg lavas of the Ventersdorp supergroup or LIP were sourced from a multiplume that was influenced by a subducted material. And during the partial melting, there was garnet control where the garnet was retained, causing the decoupling of the neodymium and hafnium isotopes. Yeah, thank you.
Thanks, Khulekani. Do you want to unshare your screen, and then we'll open up the discussion? I'm sure you'll have lots of interesting questions. Right, lots of food for thought, everyone. Chris, do you want to kick off? I see you've got a question in the chat box. I don't know if Khulekani can see it, or do you want to talk to it, Chris?
Hi, Khulekani. Thanks for the talk. I was just wondering whether you separated your steep rare earth group from the shallow rare earth group on the neodymium hafnium diagram. Just wondering whether there was two groups, and so rather than decoupling, there might be two separate groups, each with coupled neodymium hafnium. Have you looked at that?
No, I haven't separated them, but from looking into the decoupling, the two samples that are at the high hafnium compositions, they come from one borehole. So chances is that those samples they could have been representing a melt product that was highly influenced by the garnet control during the partial melting, but I haven't separated the shallow group from the steep group.
Okay, thanks.
Yeah, I've got a question, John. You don't
Yeah,
mind?
go for it, Neil. Yeah.
Okay, thank you very much for that talk. I've learned a bit about the Ventersdorp and Western area. When you go back to, don't go back literally, but your first time you showed the rare earth element plot, if I got it right, you explained the high light rare earth elements in terms of alteration and a carbonate bearing fluid. And then later on towards the end, I thought you were talking about a garnet in the source area, partly explaining that high light rare earth element trend. Is that correct?
I'm not getting you completely, but I did indicate that the enrichment in the rare earth element is due to the carbonate-rich fluids. And
Okay.
but following that, I did show that enrichment in the incompatibles did not affect the neodymium isotopes. Therefore, I attributed the decoupling to a garnet control within the source.
Okay, well, putting aside the latter part, the pattern there of high light rare earth elements and a steep trend, I just sort of question whether it's an alteration trend. It looked very like an igneous trend to me. I'm not the expert on sort of igneous rare earth element patterns. There's better people on this talk, but as far as alteration goes, I wouldn't expect it to match that type of very igneous rare earth element pattern if it's an alteration event that increases the light rare earth elements by essentially 2 orders of magnitude compared to Barberton. Just something worth looking into.
Yes, that's correct. Yeah, I concur with you that the abundance of the incompatibles within these lavas is due to alteration effects rather than magmatic signature. So yeah, I do agree with you. Yeah.
Okay, thank you.
I will look into it.
Yeah.
Okay. Khulekani, these really ultramafic, or as you say, commoditic rocks, I mean, how extensive are they? I mean, we're talking about a lip and it being big. Where does it sort of extend from in that sort of, in what you refer to sort of as a northeast southwest rift structure? Volumetrically, have you got a number or a guesstimate?
No, for the ultramafic, we do not have the extent, the special extent. But however, for the Ventersdorp, the whole Ventersdorp, we think it was almost the whole Galva craton. And looking at the previous presentation, there are intersections of the Ventersdorp far west portions of the Galva and also in the eastern sections of the Galval. So we do think that the Ventersdorp did almost cover the whole Galval craton, but for the western area ultramafics, we do not know, but from the study by Myers et al., they do show that the western area is not intersected across the whole Galval craton, probably due to the uneven topography of the basin at that time. So it is only preserved in some portions of the craton, but we don't know where, and we don't know the extent of that of the exposure or preservation.
Okay.
Could I ask a question, John?
Hi, Richard. Yeah, go for it.
Yeah, look, thanks for that talk, KK. It was pretty interesting. But there's so many questions here that one doesn't really know where to begin. But let's start off with the distribution of the Western Area Formation. I get the feeling from what you said that it occurs in more restricted areas than the more widespread, more Solitic type volcanism that had occurred later in the Ventersdorp sequence. Is that correct or not?
Yes, that is correct. Yeah.
Okay, correct. So that then homes you into a specific area where you had this high magnesium komatitic volcanism taking place. And you had some very interesting sections of core, but I wasn't too clear in your core sections. You said they lava flows. You didn't really show flow contacts, or can you see flow contacts, the bottom of a flow and the top of a flow? And also I wanted to know whether you talked about cumulate zones. You've got olivine cumulates, but you've also got pyroxene cumulates, clinopyroxene cumulates. These all occur within one flow, I take it, or are they specific to certain flows? So these are the sort of questions that one needs to look at here. Have you got any comments there, KK?
Yes, I do. So with the flows, so the borehole E5 that I showed you is that there is a cumulate zone that creates into a porphyritic zone and then into a spinifex zone. And then after that, there is another cumulate zone. So between the spinifex zone and the second cumulate zone, that's where there is a chill margin and moving into another flow.
And what is the thickness of these flows, more or less?
From the borehole that we have, one flow will be about 40 meters. The one that we have when the borehole E5 is at least 40 meters.
That's quite substantial, yeah.
Extensive, yeah, thick.
But in a very narrow spinifex zone then at the top, or near the top.
Yeah.
The spinifex zone itself is fairly narrow, is that right?
Not so, because it moves from a macro, a coarse spinifex into fine grained, maybe from about 5 meters. If yeah.
Okay, so you almost get a chill zone above the spinifex, or a flow top breccia, perhaps. Do you find that sort of thing?
And from the samples that we have, we haven't come across any breccia, because from around the spinifex, the micro spinifex, the fine grained spinifex zone, we find the pyroxene phenocryst within that spinifex zone. So it could be that, like, during the chilling, there was the new pulse and crystallization of pyroxenes forming the cumulate at that zone.
I see, okay. No, thanks, interesting questions. The other question, but I'd like others to comment as well, but is the actual terminology, and that's always been confusing. I mean, a peridotic or a komatiite, a true komatiite has 33% MgO. You're talking about rocks here with about 20% MgO, I think. Is that the highest MgO number you have?
The highest is about 24.9 something, 996. That's the highest, yeah.
Oh, is that so?
Yeah.
So is that due to more olivine being present in that rock?
As the highest magnesium oxide content that we observed was around the olivine cumulate zone and also around the Spinifex zone.
Okay, so have you got a bulk composition of each flow?
Of each flow, we only have one full flow, and the others are just partial. We don't have bulk composition for each flow.
Okay. Okay, well, thanks very much. You've added a huge amount of very interesting information. So thanks for that. Okay.
All right, thank you.
Okay, from some other questions, some of your colleagues and other students, we'd like to hear your opinions on the work you're doing relative to what KK has done. Lou? Okay, I've got a sort of bigger question, and it's probably for another discussion, and that goes back to the fact that we have this amazing Carpfel craton, and it's produced lots and lots of diamondiferous kimberlites, and those diamonds, or we have diamonds in the vits, so we had diamonds back somewhere coming out of the mantle, if we believe the sort of normal diamond source model, back around 2.9 billion years or earlier, and then we've had we have diamondiferous, or we have kimberlites at 1.7, and then we've got things like the Premier 1200, and we have more than one locality. We have same ages up in Botswana, and then we have the 550 million year Phoenicia kimberlites, and there are a whole bunch of them, and then we get back to our sort of 240 pre-Karoo and post-Karoo, 240 and 90 million year old kimberlites, and I'd be interested to hear Andy's version as well on this. My concern is that we have this model that we keep putting a bloody great plume or huge plume under the Carpfel craton, and we keep doing it repeatedly, and if we're generating that huge amount of heat, would we actually have preserved that keel, which was the important sort of receptacle for obviously diamonds, and then we kept on having these pulses of kimberlite coming through that keel and bringing diamonds up to the surface. And we know also that if we look in other parts of the world, the Wyoming craton is a classic, and we see it in India, that there's clearly evidence of keels having been either removed or delaminated. So my concern is how we keep producing all this repeated magmatism by putting supposedly a great big plume down below. And it goes back to my earlier question. I really think we need to start looking more carefully at the sort of focal points of these huge LIPs. I mean, my view, and I think there's enough evidence around the world that basalt flows can flow for miles, proper basalts, dolotic basalts. And if you actually go and look at the Karoo volcanics, the sort of thickest succession of the volcanics are actually off craton. They sort of up through the Lubombo, where we've got kilometers and kilometers of volcanics, mafic and silicic. We've got all the Lesotho basalts almost sitting around the edge or the margin of the craton. And if we look at the dolerites too, we obviously find sills and Kimberley and odd dolerites cutting the craton, but most of the dike activity, be it the Rooirand or the Karoo dikes, are actually again off the craton edge. So I really think we need to have a discussion or start looking more carefully at how these so-called massive plumes actually impinge on the mantle. Sorry, not on the mantle, on the sort of cratonic keels, where we also have our diamonds stored away. So that's just my observation. I'm concerned that four plumes sitting under this amazing craton over a great period of geological time haven't skewed up that cratonic keel and had a real negative impact on the diamond. So So I know we need lots of heat to generate all these basalts, but I think we need to start thinking more carefully from a sort of preservation of diamond point of view about where the plumes actually sit and how they impinge on these cratonic keels. So that's just a comment, thoughts that I have on this whole plume model. I really think it needs some quite serious refining, in my view. And Andy, maybe you want to comment as well if you're still on.
I can comment on that. It's Lou here.
Yeah.
So maybe I failed to make the point clear enough in my talk of last week, but you're right. The diamond, the survival of diamonds is really important in understanding the way that magmas are transported through the crust and the lithosphere. And the only thing that we can say, I think it has to mean that the conduits that brought up all of this magmatism, they must be really narrow, so as not to heat up the lithosphere where the diamonds are sitting. So that's an important conclusion about how magmas are transported. Yes, there are massive plumes down there, but when the magmas are ascending through the lithosphere and crust, they must have come up in very narrow conduits. That's my reply to your observation.
Okay, well, I'm glad to hear that, Lou. I found your geophysical diagram, and we were back then quite involved with Tom Jordan when he was doing, or we were doing. There was a lot of support from De Beers thrown in that lithospheric study, and you showed a lovely diagram last week where you can see cold Craton, but there's a gorgeous break where the bushveld supposedly sits. And that, in a sense, makes sense to me, that there was some sort of real break, old structural features where those mafic magmas were intruded through on a fairly localized basis, as you saying. Anyway,
yeah, okay, I think you're talking about that blob of red-looking stuff between the
two blue blobs
in the seismic. Yeah. We still don't know what the hell that thing is. There are really only two choices. It could be that red zone under the bushveld is warmer than the surrounding blue, or it's a different composition. Yeah. I don't think it's temperature, because if it was, then we would see high heat flow at the surface in the neighborhood of the bushveld, and we don't. The heat flow is actually quite low. Yeah. And so it's unlikely to represent a hot zone. So it's probably compositional, and exactly how that works, we really don't know.
Okay. Anyway, I still owe you a call and a discussion on my concerns.
Okay, sure.
Yeah. Okay. A couple more questions, comments before we wrap up. No. Students? Right, Henny, are you still there?
I'm still here.
Okay, do you want to just update people in terms of next week?